So, good afternoon. I couldn't make it yesterday, so I promised it would be a quick presentation. My name is Rogério de Carvalho. I'm from the Instituto Federal Fluminense, and I'm responsible for the software parts of the 14-bit set of the QB50 mission, both the ground segment and the space segment. And we work with a lot of undergraduation and vocational students. Okay, meaning that when things go right, I get the merit. When things go wrong, I blame them. So, things go wrong. Okay, that's an obvious assumption. We need to develop the software for the science unit before it comes, of course. No one's going to wait for the science unit to start developing the software. And ideally, we would like to have the most of the software that needs to control and makes the communication with the science unit ready when it arrives. Okay, when I say ready, I mean tested. Okay, and so, but what can we do? That was the question that we had originally. What can we do to make our development environment the closest to the real environment, actually to the real hardware, the real science unit? So the first and also quite obvious thing was to use finite state machines to model the behavior of the science unit. But in fact, we used the state machines not only to model the science unit, but to also model the software itself, as we could see in the ICDs. Actually, you are going to see that we put some more transitions, but no more states, because I'm going to talk about this later. The second point was to use automated tests. Okay? We come from a very strong background on test-driven development, developing industrial applications, and we believe that only automated tests can give us safety. Okay. The main point, the first point for automated tests, first is security, of course, and the second point is regression. When you insert a new functionality to a given system, you must assure that the older functionalities or the functionalities that were developed beforehand are still working. Okay? The second point was interactive and incremental development. Also, this is old for the DDD way, and this is quite important for us, especially because we work with vocational and undergraduation students. Sometimes it's very hard. We were talking yesterday. We listened to the case of Israel, where they work with high school students. We also work with the same level of students too. And sometimes it's a bit hard to pass some science concepts that you must know to implement the software. So when you use incremental development, it's easier, okay? Because you do it step by step, or as we say, baby steps. You get one small thing, write a test for it, implement it, make it pass. Go to another small part of it, make it pass. Another small part, and that's it. We've been developing that way for years, and when we started developing for CubeSats, we realized that it also worked. And of course, since we don't have the hardware simulation was the last point. The process the first thing that we realized was that one-step incremental process is quite beautiful, but it doesn't work when you have software to hardware. When you have software to software, as we deal with when we are developing information systems, enterprise systems, it's easier that small cycles of testing, writing a test, making the code, make it fast, and do this small loop, it's quite fast. However, when you have hardware on it, this interaction between software and hardware is not that easy, and maybe your loop is not that close. Okay, so we developed a two-step incremental solution, which is maybe a bit of a sim for agile developers, but for us it fits very well. So this solution is very easy. The first thing is first simulate on a pure software to software environment and then a software to hardware environment. So we model the functionality. Basically, write a transition on a state chart machine. On a state machine. Write this transition. That's the model. Since our machine was already done by for instance, in our case, the FlipX, we got the machine, we had it done. Although we had to put some more transitions, as we are going to see. But basically, you model the functionality, then you write the test for the functionality, or what are your expectations for that functionality to work. Mock the science unit behavior on a software. Okay, so you write a small test and a small functionality on software. Make it pass. Okay, run it, make it pass. Actually, on the same processor, but two memories, let me say like this, to be a bit, to talk on a bit low level. Basically, the first thing we do is to write a process as the software, the unit under test, and a second piece of software simulating the science unit running on a different process, and they communicate through a pipe. Okay? Then, okay, make it pass. If it passes, then you get this new piece of code and put it, download it, and alter it accordingly, and put it on a microcontroller, simulating the science unit. And again, you enter the usual loop for make it pass. So basically, this is the traditional incremental test-driven development way, but divided in two steps. First one, run it on a simulated software environment, and then run it on a simulated hardware environment. Why that? Again, because if you do it directly from software to hardware, you are going to treat integration details that you are not supposed to do directly. Okay? So if you do that, you are not doing baby steps. So that's the process. Okay, basically what I have just said, model the transition, write the test for a PC, personal computer, okay, mock the science unit functionality on a PC, write the code. While not working, you keep on refactoring the code, normal TDD, until it passes. If it's working, then you get that code and adapt it for a microcontroller, okay, where you use it to mock the science unit. Then you do another loop like this, but now using a microcontroller. Okay? When you do that, so why use software and hardware to simulate? Because simulating in pure software is not the same. Okay? You're not using the port, you're not using bus, you don't have buffering problems, etc., 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 etc. Okay? You can even simulate hardware problems, but it's not the same. So the best way for testing hardware problem is to use a hardware. Okay? Tools. We use MSP 430 on Launchpad, which is very simple, very cheap for simulating the feedbacks. Okay, of course, we implemented, according to the ICD, we implemented the feedbacks interface on MSP 400 using an interactive process. We use Yakindu, which is an open source case tool for designing, generating code, and simulating state machines. What is I'm going to show you? Okay. And we also developed a plugin for generating test skeletons. Okay. We use Energia, which is an open source IDE for developing on microcontroller platforms, and MSC 430 or Arduino for injecting errors. Okay. This is the now it's very quick, Mr. Chair, only pictures. This is what you already know. This is the feedbacks state machine with some more transitions that we felt like adding. I can explain after. This is a very simple state machine representing the feedbacks itself, running on the microcontroller. Actually, we developed, in fact, we developed a command interpreter. So basically, you send a command pack to one state machine and you get a response pack. Okay. This is a a simulation of sensor check, which is one of the commands that you send to feedbacks. And now comes our plugin. When you send a sensor check, you run our automated tests. But you can do this visually, okay? You can click and run a step-by-step. You can run the state machine and you can run the tests. Okay, actually everything is green, meaning that the test is okay. Now I have two students of mine pretending they are working. One for the picture. This is how it works. This is a simulation. The red state is the state being run and the results of the test. Okay, the Energia with the simply MSP 430. Okay. Conclusions. The main point of the incremental process is the progressive knowledge acquisition, which is very good for us, and easier risk control. Okay, we dominate the problem step by step. The automated tests tied to state machines allowed safer and cost-effective validation because the requirements are on the state machines. Verification because we tied it to automated tests. Regression test because if you do anything wrong, new and wrong, it's going to show up. And also documentation. Okay? And we have a closer simulation of those size units using another hardware. To finish, we are going to use, it's already working but really ugly right now, a second microcontroller to inject a series of errors on the first microcontroller. Right now, when I want the microcontroller to enter an error state which I'm supposed to test, I only have a push button on Launchpad. But this is quite simple. It means working or not working. So the problem is that someone must push the button. We are using a second microcontroller on Arduino, and we made a setup able of of injecting 32 different errors into the simulated science unit. So that's it. Thank you. Sorry.
Thank you very much. Are there any questions? Small one? Yes, there is one.
Hello. Thank you much for this very practical advice to the teams. My question would be, if other teams have troubles, would you be able to share your experience with them? Can I advise them to contact you?
Sure. Sure.
Yes, there's another question. Over there.
Thank you for the presentation. I have a question. I'm not sure if you're familiar with continuous integration scheme.
Sure.
Is it feasible to use it in hardware software environment?
Good question. We believe yes. In the point that we use the second microcontroller to inject the errors, that's our dream, our nirvana, is to do continuous integration. Right now we cannot do that. Why? Because the last thing I said, to inject error conditions, I must have someone to push the button. This is not automatic. This is terrible. The intention behind using a second microcontroller to inject different errors is exactly this. Providing that you set up the two hardwares, everything is on, it's possible. That's the next point. Good.
Okay, thank you very much. So we jump back.